experience in accreditation, certification, testing, calibration, uncertainty. I'm really very happy to have with you over here. Thank you very much. And I hope that our participants will be very much benefited from your lecture. I have already received your presentation yesterday, so I will share it after the lecture on our website. This video will also be available on our portal so that participants can be benefited even after that, and it will be available on YouTube channel. So with this, I would like to thank you. We have with us our Honorable Shri B.N. Dixit, our Director. Sir, thank you very much for being with us in all the programs at every stage of life. I hope that wherever I go, you are with me. So this is my fortunate that I am always having you. Thank you, sir. I would like to request you to kindly officially inaugurate this workshop. Over to you, sir, please.
Thank you, Astoji, Director Legal Metrology, Government of India. So you are having very nice word for me as well for the Mir Abbasi that he is working in NABL and accreditation work and many calibration and that type of things. And he is providing lot of assistance to the industry and all that very thing. So it is matter of very pleasure that today topic is on the dimension metrology. Dimension plays the very important role in every part of human lives. So uh, if you go to the manufacturer side, this dimension measurement is very important for the quality of the product, because if you will not keep the dimension of all these very things, you will find that the quality is not met according to the international practices, and our standards will be below, and our product will be not acceptable in the market as well as in the international market. The questions come that why the lot of our manufacturing product is not of international level, and a lot of products are coming from the abroad in our countries, and those products has taken place, and manufacturers are aside. So now this day it is also coming in the newspaper, television and other sides regarding the quality of the standards in our country, that even the most of the manufacturers are depending on the Chinese products. The raw material, there are all the things. Sometimes it is based on the screwdriver technology, and even vernier scale, slip gauges, and screw gauge, and so many other type of things also. You will see that if you will find in the market, it is made in Japan or made in other countries, Germany, but it is not in made of India. So we are lagging behind from many years, but we cannot take the place of those very countries who are manufacturing these with that precision and accuracy. So that is our challenge in our country, and all the peoples who are working in whether NABL or whatever things are there, actually they are assisting for the quality of the manufacturing product of the industries. So we have to see those very things also, that when we are producing, that our quality should go to the international level, and it should meet that very standards where it is acceptable at all the corner of the world, because we have lot of competition from various corner in the world, and if these things will be not resolved, so I hope that it will stuck our market. It will affect our manufacturer. It will affect our all the peoples, even the consumers also, because we will depend upon them only. And if any defect is there, then we cannot go anywhere to rectify it, because they are just selling the product and they are not rectifying or replacing those type of things. So lot of the problems are there. We have to improve the manufacturing quality of our products. I hope that today Mir Abbas Saab lecture will be in that very direction, that how to improve the quality of the instrument or dimensional measurement of the Indian manufacturers, and what are at the international practices, and where the Indian manufacturers are there, and where our laboratories are there, what they are adopting जो है, and what their further requirement is there जो है. Wherever you are the expert of NABL 17025, so that covers the lot of things, and measurement of uncertainty and all that very things. I think you will discuss on those very issue also, Jay. So I hope that today lecture will be very fruitful to the all the manufacturer, participant, legal metrology officers from the state and central government, and it will be beneficial to us also. We will also learn something new from you, because we have never think that we should never think that uh, whatever the young generation are there, they will not provide me the something better knowledge. So it is better to get the new questions and new era, and explanations ways of the people there. So we should every day we should talk with some the younger people, some 3 or 4 questions, so that we may understand that where their mind is going and what we have to improve in our sectors. I thanks Astoji, I thanks Veera Basi. I inaugurate this very seminar, and I wish for the success of the program.
Thank you,
Thank you
sir.
all.
Thank you, sir. Thank you very much, sir, for your kind and motivating words. Thanks a lot. Now, I would like to request our Honorable Shri Mihir Abbas ji to kindly deliver his talk and enlighten us with his vast knowledge and experience. Over to you, sir, please.
Yeah, thank you, Ashtoji, and thank you, Dikshit sir. I'm really grateful that you invite me for such a eminent platform, knowledge sharing platform, for delivering the lecture on, or spreading the awareness on the uh, measurement uncertainty, especially in the dimensional methodology. And I'm really appreciate Ashutosh ji and Dikshit sir. You are doing a very good job, splendid job in the spreading the knowledge about the metrology and legal methodology and related topics to the industry, and that is a free of cost, and you are doing a wonderful job, sir. Thank you. So I'll start my this thing. Yeah, yeah, hope my presentation is visible.
Yes, sir, visible.
Okay, and my voice is also, sir,
Yes, very well, very well, very good.
loud and clear. Okay, thank you. So dear participants, now today's topic is measurement uncertainty in dimensional calibration or dimensional metrology, in line with the ISO IC 17025. This today we are going to discuss or understand these things. Okay. Now this will the flow. First we'll understand, because we are talking about the measurement uncertainty. First we understand what is measurement, what are the important terms, some traceability, understanding of the traceability, then some SI about the brief about the SI units, and ultimately then what is the process of measurement uncertainty, how it is important, and how to why it is important, and how to evaluate it. That we'll try to understand. We'll take one example also. The time period is short, but I'll try to cover all these things in detail. Okay. Now, measurement uncertainty in daily life, it's very important. Measurement uncertainty is nothing but, for example, we are going from home to office. Some timing is taken. Maybe it's 1 kilometer. Example. It may not be, you cannot measure exactly 1 kilometer. It may be either you might be 900 meters or 1100 meters. Whenever you are measuring, you will get some different rating. But your reading may be related to one baseline and whether one nominal value, and around that value only it will be coming out. And that the variation which is coming out, that is nothing but the measurement uncertainty. It's play a very important role in everyday life also. For example, we are making some food. What the flour or whatever the even salt we are putting into it, some uncertainty would be there. Because of that uncertainty, the taste of the food can change. Even the doses of medicines, milligram written over there, the medicine, the strength is in milligrams. If the value is more, 50, for example, 50 milligram plus minus 2 milligram, like that. More than 2 milligram plus minus uncertainty, and if it will be more than that, it will definitely either the dose may become ineffective or maybe high. In case of high, it may be dangerous also. It's play very vital role in around us. Everything is there. It is not only it is important in the industry. It is around us. If you see in that way, okay. Now, measurement uncertainty, basically these are two words. One is measurement, and one is uncertainty. Okay. First, let me have some brief about the measurement. Then I'll go to the uncertainty, so that you will be able to understand both the words properly. Okay. Now, if we talk about, we want to discuss about the measurement. This is one of the famous quotation given by Sir Lord Kelvin, the scientist whose name is the Kelvin, and he was given because he has done a lot of research on the temperature meteorology, especially. So that's why he has been given the Sir Lord Kelvin the status. What he said: if you want to measure something, and we want to improve it, then we need to measure it. Okay. When we can measure what we are speaking about and express it in numbers, that means we know something about it. But when we cannot measure it and we cannot express it in numbers, your knowledge is of unsatisfactory. For example, somebody is feeling feverish today. I'm feeling feverish today. So it means he feeling some heat in the body. Then we need to use thermometer to measure actually the temperature of the body. Then only we can come to know whether he is having fever or not a fever. Accordingly, medicine can be given. Okay. So like this, similarly, somebody is heavy, somebody is lightweight, like that, then we can only tell once we measure that thing. Therefore, the measurement is very important. That is true in the numbers, 5 kg, 10 kg, and like that. If we can measure that thing in numbers, then we can say we know something. Similarly, measurement uncertainty. We say there is a doubt about in our measurement, that much of doubt. Doubt is nothing but the measurement uncertainty. How much is the doubt? If we can express it in numbers, then we can say we know something about it. But if we cannot measure it in numbers, well, our knowledge is definitely not satisfactory kind. Okay. Why we do the measurement? We do the measurement actually to know the exact anything. What is the status? For example, just I said somebody feeling feverish, or there are two people. Somebody says I'm more heavier than him. Okay, then how we can come to know? We need to measure the weights of both the person. Then we come measure the person, and we know the weights in terms of numbers, maybe kg. Okay, then we can say after getting the measurement observations, then we can say who is heavier than, who is more heavy, like that, who has more weights of anything. Whatever the measurement is done to know the exact status of anything, whatever is around us, maybe that could be time, that could be distance, pressure, dimension, strength, conductivity, or anything, whatever thing is around us. If and the time we are taking from the watch, today time of this present this program is at that time, so we are measuring the time, this time is there, we have to matlab, go on the online, like that. Okay, distance, how far we have to go to somewhere, we have to go to from our home to office, how far is the distance, how much we have reached, how much is still remaining, like that, anything is there around us. Okay, now something about the measurement traceability is also play a vital role here. The ultimate traceability in the field of measurement is the BIPM. That is ultimate, nothing beyond that. Okay, below that there is NMI, National Metrology Institutes. Okay, they are and below that national standards, just like a NPL, National Physical Laboratory in India, like that. Okay, NPL UK is also there, like that. In other countries, maybe some name may be different. Okay, just like a PTB in Germany, so they are the national standards there. So maybe name of the nomenclature of the laboratory, the national standard laboratory may be different, but idea is that they are just like example is National Physical Laboratory in India. Okay, national standards laboratories of that country. Then below that the chain of the accredited laboratories. Okay, uh, and for example, some lab in India is getting their masters calibrated from the NPL. So it means they are maintaining the traceability. Yeah, from the BIPM, that traceability will get completed. Then this chain of accurate laboratories. What accurate laboratories do? They do the calibration of the instruments of the which are used maybe in the manufacturing company. Okay, and then accordingly a product is being made. Manufacturing company do make the product based on the calibration of their instruments. And okay, and because of this chain ensures that their product is safe, reliable, and accurate. Because of this chain, because system of measurement is established properly, then the product of this chain is very important, because this accurate laboratories ensure the traceability system properly, and they are being audited by the accreditation bodies. It means they have their competition is verified. They are having one of the best available or relevant equipment in the industry, in the laboratory. All these things are witnessed and verified by the experts, assessors of the accreditation body. It means whatever the calculation they are doing as per the national and international standards. According, if any company get their instruments calibrated from there, so their product, whatever the product they are making, the product will be good in terms of the safety, in terms of reliability and accuracy. If you see the here, sorry, in the left side, measurement uncertainty. Measurement uncertainty will be coarser at the bottom, at the product end, and will be finer or will be less at the top side, BIPM. Here, the chain the chain will be as much as longer, the uncertainty will also be in that way. And the uncertainty means doubtness in the result. Doubtness in the measurement will be less at the BIPM level than the NMI, like that. It will bottom down, it will be on higher side, right? So accordingly, if mostly people I understand might be working in the calibration of testing laboratories, accordingly they need to decide the how if they can go towards as much as close to the national standards, their uncertainty will be as less as maybe possible in their field of measurements. Okay, or testing or calibrations. Now, SI units. There are basically 7 fundamental SI units are there. For the time is the second, length for meter, mass, kilogram, electric current. For electric current, there is ampere. Then thermodynamic temperature is a Kelvin. Generally, though we use the degree Celsius, but same thing. Conversion is there. Amount of substance is mole. And luminous intensity is candela. Okay, there are 7 fundamental SI units which are maintained by the BIPM, the basic, and other countries are taking the making the prototype from the main unit. According, they're making the prototype and getting compared with the BIPM and maintaining the traceability system in their country, like that, or tracing the main standards. Okay, just for your information, I have given since we are discussing about the length or dimensions, the meter, the definition, it's a very difficult definitions because everybody cannot understand. Even I could not understand it, but you must know it because you are working the relevant field of the measurement. Somewhat you should know whether this unit of meter exists, and what you may not be able to understand the definition of this, but how they measure it, I don't know. But they have done the system. They made a rod of 1 meter length and preserved in the BIPM. Okay, this okay. Moving ahead. Now, uncertainty. How uncertainty and accuracy play a role in the industry. The accuracy, how much accuracy, how much uncertainty would be there, like that. Wait a minute. Okay. For example, international system, because whenever you go from the top to bottom, accuracy somewhat is become close to the your uncertainty, or how the accuracy travels in the traceability system. The accuracy, for example, the highest accuracy level, it's a typical example just for your understanding, just for your to clarify these things. For example, the international standard like BIPM or NMI are having the accuracy of their master or their setup is 0.0001%. Then the national standards will be definitely coarser than this, maybe 1/10 of this national standards. Then accordingly, if we go bottom of down this, the accurate laboratories major best master available with them is of 0.001% of accuracy. Okay, then manufacturing company is product best instrument available, and the any instrument which is used at the production level is of 0.1% accuracy, and accordingly the product they are going to make it with that is of 1% accuracy. So this is a simple chain of the traceability system, how it's go from the top to the bottom. Just an example, typical example. Here also the measurement uncertainty definitely at the bottom side will be on the higher side, and the top side will be very small as compared to that. Okay, this is how it is go from the bottom to the top level. Okay, some important terms in this concept of the measurement uncertainty understanding is, first is the true value of a measurement. Measurement means, for example, measurement is a parameter which we are doing the measurement. For example, for vernier caliper, we are doing the length measurement. Okay, in vernier caliper also maybe some external measurement or internal measurement or depth measurement. It has 3 measurements: external, internal, and depth. So at the time of this measurement uncertainty, we are doing it for the external measurements or internal measurement, like that. So for example, the external measurement of the vernier caliper, it's our measurement. Okay, the true value of a measurement quantity being measured cannot be achieved. True value of something which is consistent with the definition of something which cannot be achieved, because it the true value of something will go up to the infinity, and we have a limitation. We cannot go to the infinity. So actually, for example, the length of any job is there. If we measure the length with the vernier caliper, we'll get in terms of the least count of the vernier caliper. But if we go for the micrometer, then we'll get some maybe value in the micron also. But if you go some better setup with having more decimal points, then we get the digit after that also. It means whenever we are increasing the decimal points or accuracy level of the master instruments, we are getting the value after thereafter also. So it will go up to the infinity level. That's why we cannot determine the true value. At the best, we can obtain an estimate of or approximation of the true value, whatever the value we can get it. Okay, that is maybe the best available value of that object, of that parameter. Accepted reference value, a value that serves as an agreed upon reference for comparison. For example, the value of the our standard weights, whatever values we have got from the calibration lab has it defined, that is serves as the purpose of that is accepted reference value. Whatever the in the calibrations CRM's value, certified reference material, those are working in the testing laboratory, they might be knowing this certified material. For example, any metal CRM is there. Whatever the value they have given, that is the only reference value. But if, for example, they have given 14.2 some value of that particular parameter, but after 14.2 after that there might also be value, but for our reference purpose, that is the value 14.2, like that. And that is good for the comparison purpose, because beyond that the cost will get increased. So that will not going to solve our maybe the for the purpose of measurement type is our that accuracy level, that much value is sufficient enough for us for the comparison purpose. Okay, now accuracy of measurement, whatever the accuracy of measurement is there, the closeness of agreement between result of a measurement and the true value of the measurement. It means whatever the measurement we are doing, how much we are close to towards the true value, how much, that is the accuracy of our measurement. The true value is somewhere in the measurement value. True value, how much close true value is only one. How much close we are to that true value, that is the our accuracy measurement. Our measurement, how much accurate, how much we are close to the true value. Okay. Now, some other importance are accuracy that we have already discussed, and the precision, consistency, the closeness of the repeated measurement to each other. When we are taking the repeated measurements, how much these measurements are close together. A closeness between the differences between the measurements is very less. They are close towards each other, and proximity of the true value. Then high precision means low variability, means they are very good kind of measurements. Now repeatability, short-term stability. When we are doing the repeat measurements, then the difference which we are getting in the maximum to minimum, that is the repeatability. But the condition is that same person, same operator, same method, same identical conditions in a small, in a short time duration, in the specific without time delay, means that measurement requires, for example, 1 minute to take the readings. Then you're taking the reading after one minute interval only. It is if 1 minute only required, but if you're taking the reading after 1 hour, that will not be the repeatability. That will become the reproducibility. Any variation in the repeatability conditions will transfer that value to the reproducibility. That will not call the repeatability in that case. Person may be the same, process may be the same, but different operator can be there. Even different measurement system can be there, different operator, different time, different locations, different masters can also be possible in the reproducibility. Okay, it's a generally long term, means more time difference is there. Maybe you're taking some readings today and tomorrow you're comparing the tomorrow's reading, then it will become the reproducibility. Okay. Now this is the just a pictorial uh, pictorial form of the repeatability, accuracy. Here this it is accurate. here this one is high accuracy, high repeatable, this high precision level, but low accuracy. And this is neither accurate nor repeatable, like that. Okay. Now, some other important terms in related to the concept of measurement is measured. A particular quantity is subject to measurement. Particular quantity or parameter, we are taking the measurement. So this term measurement is widely used in the when we evaluate the measurement uncertainty. In the different guidelines, it is there. Okay. For measurement is nothing, maybe the parameter. For example, we have a multimeter, which has a current, voltage, resistance, and capacitance, inductance, and many other parameters. Okay. At the time of a particular time, we are evaluating the measurement uncertainty for voltage only. So voltage is our measurement, like that. The parameter for which we are the quantity is subject to measurement, the quantity which is under analysis, or quantity which we are measuring. Okay, so that is the meaning of that. Now, error of measurement. What is the error of measurement? And measured, it's a difference between measured value and standard value. Whatever the value observed, maybe the UC or whatever you can call it, the measured instrument, and the standard value. For example, you're calibrating the weighing balance with the standard weight. Standard weight's value is the standard value, and the measured value observed at the weighing balance is the your measured value. Similarly, for when you are calibrating the vernier caliper, the value observed at the vernier reading of the vernier caliper is the measured value, and standard value of the slip gauge is the or caliper checker whichever you are using for the calibration, that is the standard value. Okay, there are sometimes some types of error we talk about, some random error and systematic error. Okay, there are two types. Random errors means those are variable in nature, is very maybe in terms of temperature or repeatability kind of thing, which we can control those errors and try to minimize. And there are certain errors are systematic, those are in the system, we cannot reduce those errors, cannot eliminate those errors, like the accuracy of the master instruments, the measurement uncertainty of the master instruments, like that. We cannot remove those things from the system. Okay. Error is one of the main contributor to the uncertainty. Okay. Error of the maybe the master instruments is the one of the main contributor to the uncertainty. Okay. Measurement uncertainty tells us how well the result of a measurement represent the true value of the quantity being measured. Means quantity being measured, whatever that quantity we are measuring, and true value tells us how we are close. Measurement uncertainty tells us how well the result of measurement represent the true value. Any true value, how close we are true value, and how the true value can be represented. That is the main purpose of measurement uncertainty, or how close to the we are to the true value. Okay. Now, error and uncertainty. These are two terms, two different terms. Sometimes people get confused with these two terms, whether the error is related to uncertainty or uncertainty is related to error. Uh, uh, just I'd like to tell you that error is one of the main contributor to the uncertainty. That is true, but error is something different, and measurement uncertainty is different. Error is the difference between the true value and the measured value. Error is the difference between some values, two values, whereas the uncertainty is a parameter which comprises the dispersion of the true values with spread to the true values, quantity which we are measuring, maybe repeatable values we have obtained. It shows the spread of those values. Okay. And error, it is the property of an instrument. Error is always related to the instrument. Instrument has an error, like, whereas uncertainty, it is the property of measurement. Uncertainty is related to the measurement, error is related to the instrument. Okay. Error is generally single value, either plus error or minus error, positive error, negative error. But uncertainty, it's range, plus minus. Okay. Many times error can be applied as a correction to a result. Sometimes plus error is there, we deduct it value and try to adjust the error. But for the measurement uncertainty, it cannot be done. You cannot apply this as a correction to a result. Okay, it's a non-negative value, uncertainty. Error may be a positive or negative. What is the definition of the measurement uncertainty given by the ISO? What it says: uncertainty of measurement is a parameter associated with the result of measurement that characterizes the dispersion of the true values, which could reasonably be attributed to the measurement. Basically, when we evaluate the measurement uncertainty, we get some plus minus value. Okay, plus minus value means the true value is lying between that range. There is a main value, then plus minus uncertainty value. The true value is lying somewhere. It's a spread. When plus minus, that's the spread of the value of the, for example, we calculate the measurement uncertainty as 10 plus minus 1. For example, 10 is our main value, then plus 1 minus 1. It's given a range, spread. And the true value is lying between that spread, that range. It's the meaning of the simple meaning of this definition. It's a parameter related to the measurement, and it's a given that characterizes the dispersion of the true values. It gives the dispersion spread of the true value. It means true value is lying between 9 to 11, 10 plus minus 1, 9 to 11 true values lying somewhere. That too, that 95% confidence level. It means if we measure the same value again and again, up to 100, we repeat do this analysis for 100 times. It means 95%, there is a probability that 95% the true value will be lying, our results will be lying this range, and 5% may lie outside our values. And this is the meaning of that. Okay. Now, in general language or general understanding, non-negative parameter, and this standard definition is given by in ILAC guide G17, and it is also indicated in the WIM 2.26. Measurement uncertainty is nothing but a non-negative parameter characterizing the dispersion of the quantity being measured to a measurand based on the information used. This is what I have told you. The non-negative value, it means always a plus minus. Okay. And dispersion, spread of the quantity being measured, attributed to the measurand. Measurements say associated whatever the values are there, it will give the spread of that. Okay. It is mandatory for all calibration labs to report measurement uncertainty. And this is demanded in the ISO IC 17025. Now, all the laboratory has to specify the measurement uncertainty. And for testing also, they need to do this also. But over calibration, it's more stringent as compared to the testing laboratories. Now, this is for example. What I try to tell you just in before. For example, there is an example of measurement uncertainty estimation done for a vernier caliper, a delta vernier caliper at 300 mm. If you see the reading what we have, sorry, wait a minute. This 300 mm range. Standard value of slip gauge is also 300. Measured value at vernier caliper also 300. It means there is no error. But we have, once we evaluated the measurement uncertainty or calculate the measurement uncertainty, it is coming out plus 0. Plus minus 0.005 mm at 300 mm. Okay, that too at a 95.445 confidence level for corrosion factor K equal to 2. What's the meaning of that? Means 300 is the baseline, this is the reading, and the measurement uncertainty is plus 0.005 and minus 0.005 means 299.995. It means the true value is lying between this range somewhere, but we don't know where. Okay, that's the meaning of that. Uh, the meaning of the measurement uncertainty. True value we cannot achieve it, but we can try to come closer to the true value like that. Okay. Now, there is some estimated value, true value. For example, this is the true value, absolute value. This is the uncertainty, measurement uncertainty value, somewhat like that. So in this range, somewhere, this is our measurement range, and true value is lying somewhere. We don't know where it is actually because we cannot measure it. Why we evaluate measurement uncertainty? Why we do this? Measurement uncertainty of a result is a quantitative indication of its quality. It means quantitative indication of its quality. It's if measurement uncertainty is, for example, 10 plus minus 5, 10 plus minus 1 is there. And this is one case. Second case is 10 plus minus 0.1. So uncertainty plus minus 0.1 is better than the 1 because it's the indication of its quality. Lesser the doubt, greater the quality. It's the meaning of that. Uncertainty value, we should strive to achieve the best possible measurement uncertainty means best possible means as low as possible, as small as possible. It's a degree of doubtness. And lesser the doubt, greater the quality. This is the meaning of that. Okay. It's a doubtness. Measurement uncertainty is nothing but the doubtness in our results. And how much the doubt we can minimize it. And how much the smallest value of the measurement uncertainty we can have it. That is the best quality. Right. So if the value of the measurement uncertainty is more, means it means the doubt is more. The quality will not be good in that way. Okay. Now, importance of measurement uncertainty in wherever we go in the industry, at the either in the manufacturing, we are making, for example, the robotic arms is manufacturing some doing some welding or making some product. If the precision level, the length measurement is not getting correct, he is not being set properly, he will not be able to do the welding at the correct point. He will misalignment would be there. That will give you the incorrect readings or incorrect product, bad products. Rejection will be more in that way. Exact fit functions meet safety standards. If your uncertainty value is small, you can make a good safety, good products, either it's a chemical or whatever it may be, it will be good products and good safety standards will be there. Even in the R&D also, if scientists measure and many things and analyze these things, if their doubt will be more, then product variability will be more. If doubt will be less, measurement uncertainty will be less. So their credibility, their confidence in the result will be more in that way. And trade and logistics also accurate weight. If weight uncertainty, suppose you're sending in some shipment and plus minus uncertainty of the weight is 10%. So 10% weight may also increase to the on the ship. If that may also be possible. If you measurement uncertainty is less plus minus 1, only 1% would be there like that. So you try to minimize in that way as much as possible. Accurate weighing is very important in the industry. Okay, and that can only be reduced by reducing the value of the measurement uncertainty, because whatever you are measuring anywhere, any process, there will definitely be some measurement uncertainty playing a role in that. You try to reduce the value of the measurement uncertainty in that. Okay, why we do this? We do it to make confidence in our decision. Whatever the decision we're taking because of the measurements, that we want to have the more confidence in that, either in say in the R&D, manufacturing, or wherever it may be. Okay, risk and cost control. If high uncertainty means it lead to wrong pass or fail, rework, recalls. Even our products also may go with the more weight like that. That may also be possible. That was the risk to the manufacturer or producer. And traceability and comparability. Measurement uncertainty is essential for comparing the results between the labs, establishing traceability to standards and supporting accreditations such as ISO IC 1725 like that. So very important. Okay. Why we do it can be used for the improvement of the measurement process, test calibration procedure, and industry process also, because whatever the measurement you are doing for the industry equipment, based on your results, they are setting their process and accordingly they are making the product. Therefore, the calibration is more important. Okay, calibration testing, whatever you are doing, that is more important. Then the results, the variability of the results or the doubtness in result has to, or uncertainty has to be as low as possible, because that would be course the industry process will also be have the component of that may also play in that way. If value is small, it will definitely going to help them. Okay, it helps us to obtain valid measurement results. Now, whatever for example, specifically in the calibration, it's very stringent. We need to we identify the possible errors, access instrument accuracy, reliable, and giving the pass fail criteria. Because of the uncertainty, how sure we are about the result, that is the criticality, and decision in making the pass and fail. It's very critical, giving the statement of conformity. Even in the testing also, this decision of making pass, because the product is being pass or fail like that, because of the and measurement uncertainty plays a vital role in that. Okay, avoid false acceptance, ensure compliance, reduce risk, risk management, everything it's come into that. Okay, there are two types of estimations, type A and type B. Type A is generally using statistics, usually from the repeated measurements. Is most of the calibrations or most of the testing, it's like that only. And type B, uncertainty estimate from the other information other than the repeatability. Okay. For example, a measurement uncertainty quoted in the calibration certificate of the master equipment used, the accuracy of the master instruments, and least count, uh, and also their least count either UC and or sometimes we are considering the master also the least count. So these things are in the system. We cannot eliminate these things. So they are sometimes systematic. Okay. Random is sometimes to be type A is considered as a random in nature, which we try to minimize it up to large extent. But 100% elimination may not be possible, but up to minimize type A up to large extent. But type B, you cannot minimize it. It will be rare, remain in the system. For minimize it, you need to recalibrate your master instrument from better calibration laboratory, having the uh, smaller value of the measurement uncertainty like that, or accuracy, better accuracy instrument you need to use it. That is the only way to minimize the type B. Otherwise, type B will remain in the system, will remain like that only. Okay. Now, what are the distribution system available with us? Because when we are doing the measurement uncertainty analysis or evaluating the measurement uncertainty for any calibrations, so we have to use certain distribution systems, probability distribution system, and first choice is definitely is the normal distribution. And when to use this normal distribution, there are conditions of the measurement systems or distribution system which needs to be used and when that need to be used. Okay, normal distribution, it is used first is the type A, repeatability. When we are doing the repeat measurement, then in that case we need to use the normal distribution. Number two, in type B, we need to use this normal distributions when the quoted uncertainty component is stated along with the level of confidence. In such cases, one is to find the value of the coverage factor so that the quoted uncertainty component divided by the coverage factor to obtain the value of the standard uncertainty. Meaning is very simple. In simple language, I have written it. When the uncertainty component or the factor which where we want to apply the normal distribution, if it is stated along with the level of confidence, then only we can use the normal distribution. In such case, when component is specified the level of confidence, then we have to find out the value of the coverage factor K, so that we can divide this value of the measurement uncertainty component with the K factor to obtain the standard uncertainty. Example is the measurement uncertainty quoted in the calibration certificate of the master equipment. Okay. For example, the calibration certificate of your master is given is the, for example, the 1% example. Uncertainty is plus and 1% is given. Then you can convert that into the unit of that, then divided by, or maybe if you want to consider the percentage itself, that also be possible. 1% divided by the K. K may be 1.96 or 2, like that. Divided by 2, then that value will be converted into the standard uncertainty, and you can take it further consideration. Okay. Second distribution system is the second choice is the use of rectangular distributions. It is also one of the commonly used in the type B. When to use it? The condition to use this rectangular distribution system is that when the quoted uncertainty component is not stated along with the level of confidence, only upper and lower limits are known. It means some value is given, upper and lower limit is given, but we don't know the confidence level. For example, the accuracy of the master instruments is specified by the manufacturer. For example, the accuracy said, we said accuracy is accuracy specified by the manufacturer is plus minus 1%. But he did not specify the confidence level of definition of defining this accuracy plus minus 1%. It's a straight line, means always straight throughout the range, like that. In such case, upper limits is to be known, plus minus 1%, upper and lower limits, these are known, plus 1 and minus 1, like that. In such cases, quoted uncertainty component divided by the square root 3. In such case, so we need to divide the value of the plus minus 1% divided by root 3. Because we don't know the confidence level, this is the use of the rectangular distribution. This is how we use it. Accuracy equipment, least count, like that. Okay. Now, another type of distribution is the triangular distribution. When to use triangular distribution? When we know the minimum and maximum, and most likely the center. In the previous case, the rectangular distributions, for example, plus minus 1 is given, then it's a throughout. But in such cases, it is reasonably known that the value of the maximum value will be there at the center, not at the throughout the range. Example is the volume measurement. When we do the volume measurement, either it will be concave curves or convex, like that. So actual value may be lie at the center, like that. So this is the situation where we don't have the confidence level. We only manufacturer define something, but the confidence level is not defined. In such cases, we need to use the rectangular triangular distributions, and in that root 6 will be the dividing factor. Okay. Some other type of distribution is a U-shaped distribution. It's hardly being used in the field of calibration. Very uncommon, because I have not used it, but this is one of the used is there. Here, in such cases, value is expected to be at the corners. For example, we are doing some measurement at the corner. Its value is supposed to be like not at the center or in between. Okay. very uncommon kind of a distribution system. Just yeah, I thought you should know it. That's why I'm sharing it. Okay. Now, confidence level. Sometimes people understand what kind of confidence level we should use. Actually, confidence level is linked with the coverage factor and effective degree freedom. It is linked with that. Okay. Internationally, it is fixed to use 95% confidence level or 95.45, which are marked here. These two only are to be used because all lab has to work with the same confidence level. If you are using 95% exactly, then your coverage factor would be if depends upon definitely degree freedom, but directly related to this is 1.96. If you want to use the approximately 95% confidence level means 95.45% is the meaning of that, then your coverage factor will be 2, like that. It's nothing but a confidence level. It is the level of the confidence at particular coverage factor. Is specific coverage factor, what is your confidence level? It is generally given from 95 to 99.7, but for the calibration testing laboratory we need to use these two only. Okay. Now, degree freedom. Degree freedom is also required to use which kind of what will the number of the coverage factor, because it comes from the student T distribution table from the effective degree freedom. Now, but for effective degree freedom, we should know the degree freedom for each and every component. Okay. For example, a type A, the degree freedom of type A would be n-1 and is number of observations -1 for the type A. If you have taken the 10 readings in the type A repeated measurements, then your degree freedom will be for type A will be n-1, 10-1 is equal to 9. Okay. Then similarly for type B for each and every factor, UB1, UB2, UB3, UB4, UB5, like that, you need to evaluate, you need to evaluate it or find the degree freedom. For type B is infinity for each and every component. It is the infinity because we know the upper and lower limits in such cases. So it is as per the international norms and international guidelines, it will be the infinity. For UB1 infinity, UB2 infinity, UB3 infinity, UB4 infinity, like that. Okay, like that. And the coverage to estimate the value of the coverage factor. To estimate the value of the coverage factor, coverage coverage is how the value of the y, value the combined uncertainty, value the estimate the standard deviation. How we are getting it? We give the measure for estimate of the standard deviation. For normal deviation, effective degree freedom, which is appropriately by an appropriate. Sir, Ashutosh, some people are writing that my voice is not clear. Are you getting my voice clear? I think.
Yes, sir. For me, it is clear. There may be some problem with him.
So, those are writing this. Please check your connectivity or your mic setting.
No, right. No, I think maybe just for fraction of second it was there was a difficulty. Now it is okay.
Yeah, this is a technical things.
Just for fraction of second. Otherwise, it is okay. Please continue, sir. Please
Okay,
continue.
thank you, sir. Thank you. Which is by an appropriate combination the different uncertainty contributions. The effective degree freedom for all the degree freedoms is okay. Thank you, Prabhakar ji. Confirmation loud is my voice is clear. So this is the formula. UC power 4. This U means first value is the UC power 4, and then summation of the all the values of the UA, UB1, UB2, UB3, like that. All the combination of that. I'll share one example in which I'll try to I'll give you how to calculate it. Okay, this will be give you the more clarity on that thing, which is a very dry topic and dry subject. Okay, now let's move toward the one of the example how to calculate the measurement uncertainty. Okay, let's to my understanding, this measurement uncertainty is calculated in the same 7-step process. Okay, step 1, define the measure. What you are measuring, what parameter you are measuring, define that. That is step 1. Number 2, identify the uncertainty sources related to that measurement. What are your key contributing factors, key uncertainty sources, or key sources according to which your measurement may get directly indirectly impacted, or maybe vary because of those components. Or for example, length, for the length is temperature is one of the component. If temperature rises, length will increase, like that. This is one of the example. Okay, number 3, quantify the uncertainty sources, type A or type B. You need to quantify the whatever the uncertainty sources you have identified in step 2. You have to quantify, give them the value. For example, you identify the uncertainty source is the measurement uncertainty to master equipment. Then quantify what is the value of the measurement uncertainty specified for the in the calculation certificate of the master equipment, like that. Okay. For example, another example could be the least count. In step 2, identify the least count of the UC. Then in step 3, you need to quantify what is the value of the least count. For example, vernier caliper may be 0.01 mm. Okay, this could be like that. Okay, next step number 4. Step number 4, convert these standard uncertainty using appropriate distribution system. Now here you have to convert the quantified sources into the standard uncertainty by applying the suitable distribution system, either normal, rectangular, like that. Okay, once you did that, okay, then calculate the combined uncertainty. You need to combine all the uncertainty component which you have done the analysis, or convert them the standard uncertainty into the step number 4. Step 6, calculate the expanded uncertainty. And step number 7, reporting the measurement uncertainty. This 7-step process to, as for my understanding, this is the best of my knowledge. Okay, and let's take an example. For a dimension measurement, take one example, though I have given the basic understanding of all the processes or all the requirement of the measurement uncertainty. Let's take an example of vernier caliper. Step 1, it says step 1, define the measurement uncertainty. Example, vernier caliper. Vernier caliper, what the master instrument being used here, what the range, what the temperature conditions, what is the humidity, like that, and parameter to be calibrated. The measurement, exact measurement is the error in the external jaws or length measurement. This we are doing this for the external jaws. Okay. Now, next step number 2, for the dimensions calibrations of the or vernier caliper calibrations is there are the 7 are the identified sources. First is the repeatability of the measurement. Second is the uncertainty due to the measurement uncertainty quoted in the master instruments. For example, the slip gauge, which I have used here. Third is the uncertainty due to the master accuracy, the accuracy of the slip gauges here. And fourth is uncertainty due to the resolution of the UC. And the resolution of the UC means resolution of the vernier caliper. This is step number 4. Step 5, component number 5 is uncertainty due to the soaking difference between master and UC. Because master and UEC, they are the made of some assess stainless steel, some material, steel material, and because of the temperature difference, so the one may contract, one may expand like that. That also I have considered. Uncertainty. Okay, number 6. Uncertainty due to the difference between coefficient of thermal expansion of the material. Definitely the coefficient of the uh, thermal expansion, because of temperature they will expand like that. If temperature is more, then they will expand. If less, they will contract like that. Uncertainty due to the temperature monitoring device. Whatever the temperature monitoring device we are using to measure the temperature in the calibration lab of the dimensions calibration lab or dimension, because of that also there would be some difference in the temperature, some variability of the temperature could be there. So that also we have considered here. So there are the 7 identified sources in step 2 for the vernier caliper calibration. Now step 3, uncertainty sources identified, which we have identified earlier. Now we are giving the quantification, quantify the uncertainty sources. For example, first we have identified as the repeatability of the measurement. So standard deviation here I am writing here 0.03162. How we are getting it here, from here, repeatability. This was, there were the 10 repeated readings. The average has been calculated. Then standard deviation also being calculated using this formula of the standard deviation. So this is how we calculated the to quantify the value of the repeatability, which is the step number 1. Okay, factor number 1. And then uncertainty due to the measurement due to the MU of the master instruments reported in its calibration certificate. Slip gauge accessories 0.8 microns and slip gauge is 0.11 microns. These were quantification of the values. These are quantified, the value of the master instruments calibrations taken from the calibration certificate of master instruments. Then uncertainty due to the master accuracy. Slip gauge accessory accuracy is 0.9 microns and slip gauge is 0.29 microns taken from the manufacturer's data. Okay. Uncertainty due to the resolution of the UC or dial caliper which we have used, having the least count is 0.01 mm. Okay, these are the quantification of this factor number 4. Then factor number 5, uncertainty to the soaking difference between the master and UC. Deliberately, I have taken here the different thermal coefficient of expansion of the master and UC just for doing some calculations and analysis. If you have the same of the as here, I have taken the tungsten carbide slip gauge set. If tungsten carbide would be there, its value is different. The thermal coefficient expression will be different, and slip gauge accessory is steel, and UC is definitely assess or steel. They are having the same, but slip gauge has a difference. So if some difference is there, this is the value of the difference. Okay, and if you want to take out the average of the alpha or the thermal coefficient expansion is this much, and value of the lab temperature is 20 plus minus 1 lab is maintaining, and the actual standard start temperature is 20.4, and at the end it is 20.2, and difference is only 0.2. So this is the quantification of the values of the related to the identified uncertainty source number 5, which is soaking difference between master and UC. Okay, now further in the quantification is the 6th component is uncertainty due to the difference between coefficient of thermal expansion of the material to the master and UC. The same which I have already just before discussed, what's the value of the thermal coefficient of expansion of different materials. It's given over here. UC is steel, and slip gauge is also as a stainless steel. Then slip gauge is of tungsten carbide, and difference and what's the difference is coming out for difference and the average. Okay, temperature values are also given. Now factor number 7, uncertainty due to the temperature monitoring device. The quantification is there, whatever the uncertainty quoted in its calibration certificate is 0.1 degree Celsius and its accuracy is 0.1. Okay, so these are the quantification for the factor number 7. Now let's move to the step number 4. Convert these two into the standard uncertainties using the appropriate distribution system or analysis. Okay, for example, these are the 10 readings taken for the external jaws of the vernier caliper, and this is how the being average has been taken out, then standard deviation has been taken out. The standard deviation value is 0.003162. This is in this example. Okay, once we have done this, or if you want to report for the other external internal kind of thing, that is also possible, or different points you can take out the readings. But for specifically for the measurement uncertainty, we have repeated readings I have shown you like that. Okay, now average of all 3 readings also you can take whatever the way. Now is type A standard uncertainty, standard deviation. The how to calculate the standard deviation, uh, standard uncertainty for the type A is the standard deviation divided by or n number of readings and square root of that. This is the way how to calculate it. The number of readings are 5, so because of this we got this value. Okay, now degree of freedom for type A error is n minus 1. N is 5. 5 minus 1 equal to 4. So this is how we calculate the type A. Okay, now for is for this value, type A, step number 4 for the type A. Now step number 4 for type B. Type B, uncertainty due to the master equipment used, UB1. Master instrument used, uncertainty of the master instrument. What is the master instrument? We are using slip gauge and slip gauge and uh, accessories. Okay, so the value and the value we are getting from the data should be taken from the visibility of the master instruments used. The uncertainty values, we have combined these values 0.5 from the slip gauge accessories and slip gauge set. The value is coming out 0.5 like that and divided by 2. Sorry, this by mistake it is written in degrees Celsius. Actually, it is uh, mm, in microns. Or if we take out the accuracy like this, accuracy of the master instruments used 0.9, which was the accuracy of the slip gauge accessories, and the 0.29 was the accuracy of the slip gauges we have used. And since we are using this is type B and considering the rectangle distribution system, divide by root 3. It is divided by root 3, then this value is coming out 0.5459 microns. Okay. And degree freedom, as we have already discussed, the degree freedom for the type B component is uh, uh, infinity. So degree freedom will be infinity. Okay. Further to next component, the uncertainty due to the resolution of the ULC. The resolution we know 0.01 mm was the resolution. Divide since we are considering the it's a analog one, it's a dial type vernier caliper, so we need to consider the 25% for analog. In case of it would have been the digital one, then 50%, or vernier scale type, it would be 50%. So 20, it's a dial type. We are considering 25%, the resolution divided by 4 in 2000 for the multiplication into the microns from the mm, and divide by root 3. Root 3 is nothing but the considering the rectangular distributions. So we are using the root 3. Then once we do this, calculations, it will be 1.4434 value will become in the microns. And degree of freedom is we have already discussed. For type B, it's infinity. The degree of freedom for this component is also infinity. Okay. Now, next component is uncertainty due to the soaking difference between master and UVC. Okay, master and UVC. Since we know this is the formula when we are using the thermal coefficient of expansion or taking out the contribution from the thermal coefficient of expansion, the formula is definitely the temperature difference and the alpha average and the maximum range of UC. This is the length, then thermal coefficient of expansion and the temperature. Once we multiply these things, all will come into the that required unit. It will get it in terms of microns. And the 1000 being used as multiplier to convert into the into the microns. And root 3 we are using here as a distribution factor because we are considering it as a normal distribution. It's a part of the type B, and the delta T is 0.2 is given over here. Is the 0.2, and the alpha average we have taken out is this value 0.00000092. It's a alpha average. Okay, and then 300 was the length which we have considered. Maximum range of the UC or the length which we are calculating, and the 1000 multiplier for the to the microns. Okay, and divided by root 3 a normal distribution. When we do these calculations, we'll get the value of 0.3199 microns. This how the UB4 will be calculated. Okay, now a degree freedom, definitely the infinity again. All the type B components, it will be the infinity. This is how we got the UB4. Now move to further explanation of the linear expansion equation. Delta L, change in length, is calculated using the formula into alpha into L, original length, and delta T. This formula we have used. This is nothing but the linear thermal expansion is change in length of a solid material when heated or cooled is equal to the linear expansion coefficient for that material multiplied by the original length multiplied by the change in length, change in temperature, like that. This is the meaning of that. Okay. So, and the thermal coefficient of expansion for a typical vernier caliper, usually made of the steel, is around 11.5 Newton per minus 6 per degree Celsius, meaning for every degree Celsius increase in temperature, the length of the caliper will expand by a very small amount, approximately 11.5 into 10 power minus 6 of its original length. Okay, this is the meaning of that. Okay, now UB5. UB5 was nothing but the standard uncertainty due to the difference between coefficient of thermal expansion of material and the master. Material means the UC and the master, because the difference is 0.000068, because UC is 0.000000115 and the slip gauge is 0.00000047. Okay, so difference is this. So then again in the same formula we'll use it here. The alpha difference temperature limit we are considering the maximum limit, because the laboratory is maintaining the temperature within the laboratory is plus minus 1. So maximum it can be up to plus minus 1, and the difference would be there in terms of that value, and 300 is the length, and 1000 the multiplier to convert into into microns. Again we are using the rectangular distribution, so this how it will be calculated, and we'll get the value of the UB5 as 1.1778 microns. Okay, if thermal difference is 0, then the 10%, if suppose you're getting the same value of these, you're using the SS made slip gauge set, that then in that case you need to consider the 10%, because you cannot eliminate this, because that would be the variation would be there. Okay, now next move to UB6. This UB6 is uncertainty due to the temperature monitoring device. In short, it can be called as TMD. Okay. Here, I use the combined effect, cumulative effect of the uncertainty and accuracy here, and alpha difference. The combined effect of the temperature, TMD, uncertainty and accuracy, and the alpha difference and the maximum range of the VUC 1000 same, but only the temperature has been taken over here. The same point, the difference is taken from the previous information available, and range is definitely the 300. This is the maximum value. It cannot be more than that. Okay. A safer site has been considered. The considering the rectangular distributions. Again, it's a part of the type B, and considering the rectangular distribution, this value will be divided by √3, and we will get the value of this much. Okay. Degree freedom, again, it's infinity. Okay. If this value would have been the difference, it would have been 0 if you are using these slip gauges of the stainless steel made, then 10% you should have been considered here. This the 10% of the value. Okay. Then this how we have calculated the UB1, UB2, all the UB6 and the type A also. So now we need to go for the step 5, calculation of the combined standard uncertainty. This we can do by adding the type A type A and type B. Maybe a cumulative impact of the type A square plus type B square also can be taken, and we can also take the individual type UA1 square UB expanded form. This is UA, this is UA, this is UB1, UB2, UB3, UB4, UB5, and UB6. This also this way also we can do individually component we can write it. For example, yes, here UA square is suppose this value, UB1 this value, UB2 this value, UB3 this value, like that. Whatever the values we are getting here, we can combine all those values here. Okay, like point UB6 0.166 from taken. For example, this. Yes, 0.1 666 like that. Similarly, the UB 0.166 UB6. Similarly, all the values are taken from the different components considered here: UB1, UB2, UB3, UB4, UB5, and UB6. Okay. Now, and once we do the root mean square values, mean a square of the all the values, square of the UA1, UB1, or repeatability, or UB1 and UB2, UB3, UB4, UB5, UB6, and take out the square, then add all those values, and under square root of the all the values, then it will come out 2.2498 like that. Okay. This how this value will come, the combined uncertainty value. Now we need to calculate the effective degree freedom. Earlier, what we have done, we have calculated the degree freedom for each and every component. Okay. Now we have to calculate the effective degree freedom. What the formula which I have already shown you before, that was the combined formula. Okay. The expanded form of that combined formula for effective degree freedom is UC power 4 divided by UA power 4 divided by n minus 1. Okay, here n minus 1. N minus 1 is number of observations are 10. Okay. Number of observations are 10. So 10 minus 1 is 9. And UB1 power 4 divided by degree freedom of the UB1. Degree freedom of UB2. that is also infinity. UB power 4, UB2 power 4 divided by the degree of freedom of the UB2, UB3 power 4 divided by degree of freedom of UB3, UB4 power 4 divided by degree of freedom of the UB4, UB5 power 4 divided by degree of freedom of the UB5. Similarly, UB6 power 4 divided by degree of freedom of UB6. Since the degree of freedom of UB1, UB2, UB3, UB4, UB5, and UB6 are infinity. When these values are the infinity, okay, when these value are the infinity, so those values become any value divided by the infinity become the zero. It means this will also become zero, 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 this will also become zero. All the UB1, UB2, UB3, UB4, UB5, UB6, they all will become zero. Okay. Then then UA की power 4 divided by I. Okay. So this value means UC power 4 divided by this value. UA की power 4 divided by 9. When we calculate these values, okay, then we get the value of the 102 point something using of all these for these values. Since this value is 102, means this value is more than 30. If this we get the value of the effective degree of freedom is more than 30 as per NABL 141, that is considered as the infinity. Okay, I'll tell you how. This is the student's T distribution table given in the NABL 141. Okay, NABL 141. What it says, these are the effective degree freedom values. The left side. Degree freedom values given the left side 1 2 3 4 5 30 like this. Okay, if value of the effective degree freedom is 30, then we need to consider the value of the coverage factor from here. Okay, but if the value of the degree of freedom, effective degree of freedom is more than 30, it is considered as the infinity. Okay, when this value is the infinity and we are considering this value of the coverage factor, we are using the confidence level is 95.45. It means values this confidence level is 95.45 and infinity means coverage factor is coming out to be 2. In our case, coverage factor will become the 2. So this is how the meaning of that. Okay. So 2 is coming out like this way. So our case is K equal to 2. 95.45 confidence level is 2. Okay. So this is how we have arrived for in our case. It means whatever the value we are getting for this calculation, effective degree freedom, since the value of effective degree freedom is greater than 30, then we can consider the value of effective degree freedom is infinity as per NABL 141. When this is infinity, infinity means we have to consider the coverage factor K equal to 2. When K value is taken as a 2, means expanded uncertainty or overall uncertainty for our calculations or our the calculation expanded uncertainty for dial caliper at 300 mm is this simple step is that is step 6 is and either we can call it as expanded uncertainty or measurement uncertainty, overall uncertainty, like that. Whatever the term is same, meaning is same. The formula is simple. U is is given by the K coverage factor multiplied with the combined uncertainty. So combined uncertainty which we have evaluated earlier, we need to multiply it with K factor. Okay, combined uncertainty we have calculated here 2.2498. We have already calculated here combined uncertainty. it means we have to multiply this value of the combined uncertainty with coverage factor k equal to 2. Then we'll get the value of the expanded uncertainty or overall measurement uncertainty. Okay. Then what we get 2 into 2.2498, this value will get it, and the uncertainty value will be plus minus 4.55 microns, or we can say plus minus 0.005 mm to put it into the round of figure. Okay, to make it the round of figure 4.55, since this value is more than 4.5, I made it a round of 5 microns. Okay, 5 microns is
This guy, what do you think?
0.005.
After now, today he fucked too much.
All are requested to kindly switch off their mics.
No, Imam. Sir,
All are
this guy
requested to kindly switch off their mics, please.
how to go, bro? Wait. Call. Madi, Madi. This time leave it, okay? Next time we check. Okay.
Mr. Paul, please.
I have removed him. Don't worry. I have removed him from the meeting. Please continue.
Okay.
Thank you, sir.
Okay. When we are about to end something, then we will start at this. Anyway, thank you, sir. Thank you. And the step 7, which is the last step of the total this analysis or measurement uncertainty estimation for the dial caliper, the reporting part, which laboratory need to report in the calibration certificate. When they are reporting the measurement uncertainty, they always report along with the confidence level, along with the coverage factor, value of the coverage factor, which they have evaluated for this range. Now the term has been come of the evaluation here, means you need to use your knowledge, technical knowledge, judgment to get that value. Okay, not a simple calculation a plus b equal to c like that. Okay, then you need to report it measurement uncertainty for a vernier caliper at 300 mm is plus 300 plus minus 0.005 mm at 95.45 confidence level for a coverage factor k equal to 2. This is how you need to report it. Please remember this, you need to report the value plus minus this and the along with the confidence level and coverage factor k equal to 2. If you are not reporting this way, that will be the incorrect way of representation of the value of the measurement uncertainty. Okay, if we want to give this value into the terms of the budgeting, which is also very essential thing to make a budget of the measurement uncertainty. In the generally one pager budget is preferred to how to represent all these component, all these calculations in just one piece of paper, maybe 1 page or 2 pager. Generally 1 page is possible if you can accommodate the information properly. For example, this way standard uncertainty for this vernier caliper, if you see UA1, UA2, UB3, all these values are given. Uncertainty the master, accuracy of the master, resolution the UC, shocking difference temperature, difference in coefficient. All these values are given over here. Okay. Standard use, which as per the standard we are using, which resolution the vernier caliper you are using, the estimate of the values, what we are getting it. Then how we are, then normal distributions, for which component we are using the normal distribution. Only U1 we are using the normal distributions, and the UA also we are using the normal distribution. These are the two conditions where we are using the normal distributions. Okay, U1 means uncertainty of the master equipment, and UA where the repeatability is there. Here only we are using the normal distribution as I explained earlier. Okay, rest other cases we are using the rectangular distribution. Rectangular distributions in UB2 or U2, U3, U4, U5, U6 like that. All the components are considered as a rectangular distribution. When rectangular distribution means root 3 dividing by the root 3. All those values are divided by the root 3. Okay. Then the certainty coefficient all the cases 1. The value type A we calculated the value like this, and ultimately uncertainty value is coming out like this. And all the components either master uncertainty, this value is coming out in standard uncertainty is 4038 UB2 5459, like All these values are listed over here. Okay, in the budget, in the standard form. This is the standard form of the uh, uncertainty budget. Serial number, sources of the uncertainty, the estimate values, some limits, then probability distribution, which distribution system you are using. And you can also specify here k value, for example, here which probability distribution you are using, rectangular 3 or dividing factor which you are using. You can also specify over here. Okay, just like we are using defining over here the top. Then standard uncertainty u xi, what is the value of that in what related to that particular component. Okay, and sensitivity coefficient, if you are if you all the values are in the same unit, then you need to use the sensitivity coefficient as 1. But if values are being converted from one unit to another unit using some relation or some standard formula, then that is then accordingly you need to apply the relevant sensitivity coefficient. Okay, once this value is multiplied with sensitivity coefficient, then it will become the standard uncertainty, or in this form it will come out. All these values there, then degree freedom. All the individual degree freedom are reported over here. Like this, if you see 9 is degree freedom for the type A, 10 minus 1, and this how degree freedom, all these things are reported in the this uncertainty budget. And combined uncertainty is being calculated using the formula given the below. All the combination of all the square of all these values, adding, then is taking the square root. So this is the formula for the square doing this calculating the combined uncertainty. Okay, or maybe just written over here just for a reference. UC power UC is u1 square, u2 ub square, and ua square, like that, and the square root. This is the simple formula. Effective degree freedom, this the formula is again I am writing here in the budget form how to calculate it. UC power 4, then ua u power 4, ub power 4, and ua power 4 divided by the number of that n minus 1, the degree freedom. Then here 95.45 confidence level and k value is coming out this 2 actually for this degree freedom is calculated here again. Before this we have calculated degree 10248 something like that. Okay, so this is also depicted over here list in the uncertainty budget sheet. Okay, then reporting, and expert and uncertainty is reported with the combined uncertainty into k equal to this much, and that's in rounded form. Expert uncertainty u after rounding is 5 microns plus minus 5 microns, or 0.005 mm plus minus. So this is the way of representing the all the components, all the things in the uncertainty budget. So I've given you the brief of from the start to the why uncertainty is important, how the uncertainty is plays a significant role in the metrology, and then how to calculate it, what are the relevant topics, relevant distribution system, what are the basis of how to do that, then come how to calculate it, and the how to combine, how to represent it in the uncertainty budget form. Like the everything is I have given over here. And now if now this is almost over now with for the time. If somebody has a question, a couple of questions I may can take out for the relevant topic. This is Rashtoji. Hope I've been able to deliver the topic in time, and certain questions we can take up now.
Yes, sir. Thank you very much. It was wonderful presentation. One of the, yeah, I know very well about you and your presentations. I will share these PPTs to all the participants. And
Yes.
even after this program, yeah, anybody can ask the questions, can raise the issues on our WhatsApp group and anywhere else. We will discuss it with the participants or with the experts, and can again share it in the group.
Yes, yes, yes.
Anyone?
Certainly. Yes, anybody can
Otherwise,
other questions? Yeah, please.
Thank you very much. We will meet
Couple of
again because it
questions.
is very technical and very good, because uncertainty
Yes.
calculation is one of the very important part. And most
Right.
of the uncertainties, the process is the same, procedure is same, You just have to check whether you are doing for volume, whether you're doing for mass, whether you're doing
Yes.
for length or flow, whatsoever it is. But the basic concept behind it is the same. So my request to all the participants, I think that these type of technical programs are very important for the laboratories, for the participants, or for the industries who are doing this uncertainty and everything. With this, I would like to thank our Honorable Dikshit sir, Mehir Abbas sir, and
Ji.
all the participants. We will again meet next week on next Saturday at 11 o'clock. Thank you very much.
Yes.
Thank you all.
Okay.
Namaskar.
Thank you. Sir. Thank you.
Thank you. Yes, few of the photographs. My request to all the participants, if you can switch on your video. Thank you. Thank you very much.